Right, guys, today we want to look at the graphs of trigonometric functions, but in particular we're going to look or analyze thoroughly the curve of the sine function and try to extend that discussion to other functions. So our first, we're going to look at this kind of expression. That is the simplest form of that function is to write it as y is equal to a is equal to omega t. Now, a and the omega here, those are things I can call some kind of parameters. Omega here, I'm going to call it angular velocity. Angular velocity. And in this case here, I emphasize, I'm using t there, and I want everybody here now to assume that we're using the new radian measure of angles. Are we together? It's okay. Then our a here. Our A here is our amplitude. Right. So now what we're going to study in this simplest form, this curve in this simple form, is the influence of omega and the influence of A. But I think we're going to start with A first, then we go to omega. Are we there, guys? Okay. Now let's see. I suppose, I don't know whether I'm right, but I suppose that everybody here knows that the sine curve. Some of these things, guys, it's just revision. Is it right? It's just maybe going a little bit deeper into things, but it's revision. So I assume that we're parting from the fact that we know that sine curve is a function which is shaped like this. And in our old system using degrees, we know that it's 0 degrees here, it's 180 degrees here. But now that we're using radian measure, what are we going to write there? Pi. Good. Pi. And then somewhere here is going to be 2 pi. After that, the same kind of shape is going to repeat itself periodically, because the period of this function is actually t equals to 2 pi. Are we together? So that is what I can call there, and the amplitude now is the highest point there. We know is equals to be 1, and then the lowest again is going to be minus 1. But we just say the amplitude is 1, and then the function is written as y is equal to sine t, and then the angular velocity will also be 1. Are we together? For the standard curve like this, capital letter A, amplitude is 1, angular velocity is 1. Are we together? Okay. Now for our discussion, let me draw a new system of coordinates here. Let's say we've got our vertical axis there, y, and then we've got our horizontal, and then I will do it this way. Let me say this is pi, and this is 2 pi, this is 3 pi, and then maybe this is 4 pi. Then somewhere let's just make a mark there and say this is 1, this is 2, minus 1, minus 2. This side you can also say minus pi, and so on going that side. All together. Now what is very important for me, for people to be able to maybe plot different variations of this curve, that I think I should highlight 2 aspects here. First of all, look at this function. Somewhere here, there, and there, the value of y is 0, isn't it? Then we say that function has zeros. Let's write there. Zeros at 0, at pi, and at 2 pi. Altogether. That is important. We'll see how we're going to use that. Altogether. Okay. Now, if I now get a function like y is equals to, let's say is equals to 2 sine t. What has changed there from the standard function? The standard function, remember I said the standard function is y is equal to, let me just write it there. The standard one, it's going to be y equals to sine t. I mean, by standard there, I mean just the simplest form of the curve. Not really the standard, but the simplest form of that curve. It's equal to y sine t, where the amplitude is equal to 1, the angular velocity is equal to 1. Then we get something like this, isn't it? Now the question is now, when we get something like this, what has changed here? The amplitude, isn't it? So now, we're saying here, our amplitude is equal to 2. Then we want to see, how is the curve going to change? Is it going to change its zeros? The zeros are going to be still at 0, pi, and 2 pi, isn't it? So now, let me take that color there and say, I'm still going to have zeros there, and the zeros there, and the 0 there. But the other important thing about this function, I think I want to call turning points. Let me write the TP for turning points. Altogether, turning points are those points where, like from example here, the function was growing and suddenly it's going down. So there's a turning point there. And everybody can see, I think it's halfway, isn't it? Halfway that kind of cup down shape there, which means that is what? Pi over 2. Now for a curve like this one, if we just cancel 2, this curve is not going to be different from the standard one, is it? So which means again the turning point is going to be pi over 2. So let's plot that. Let's plot that pi over 2. Let's put pi over 2 there. Another turning point will be somewhere there. Are we together? What's the number there? It's pi plus half. Pi is 2 halves plus half is 3 halves, isn't it? So it's 3 halves of pi. So which means that is going to be somewhere there. 3 halves of pi. So as you can see, I've checked my turning points. I've got them there. Now if I were to stretch this curve longer, beyond 2 pi, beyond 4 pi, I should remember that this function is periodic. Those values are going to repeat every 2 pi. Is it? Okay. Now to plot this graph, I already know that this is on the curve. The other thing is at half pi, I know that it's going to reach the highest point, which is 1. That is the value of sine. But the amplitude says 2, which means I multiply 1 by 2. What am I going to get now? I'm going to get 2. Altogether. So which means now that the turning point will be somewhere there. And when I come this side again, it will be minus 1. But minus 1 multiplied by 2 is going to be somewhere there. Are you following that? So now if I'm going to draw the curve now, I'm going to have something like this. Which is negative amplitude. Okay, I put it wrong there. So somewhere there, ne? Okay, I think it was just simple pen there. Okay, Then I will write there, then it will go down, check the usual 0, then go down, then come there, and you continue somewhere there. Altogether. Okay. Now, if you compare that, there is a bit, the shape is not very nice there, but I hope you understand what's happening there, isn't it? Now, the normal curve, let me try to write the standard curve for that one, the simplest curve, sine t. It will just go altogether. So now, here, what I'm trying to highlight, to see the effect of 2 altogether. If we change that 2, maybe in the next instance, we write y equals to half sine t. So instead of getting the usual 1 here, it's going to get half, isn't it? And then it's got the usual 1, it's going to get half. So which means the curve is going to, the curve now is going to go not very high and not very low. Altogether, guys, that is the effect of the amplitude. Is that clear to everyone? I think that is the simplest one. So now, I now want to move to the effect of the angular velocity. So here, everybody we can just sing a song or a chorus of some sort that the higher the amplitude, the higher the wave, isn't it? The lower the amplitude, the lower the wave. That's the chorus you can learn from there. Are we together, guys? Okay. Let's see if we can get now to analyze what's the effect of the angular velocity. I'm saying now let's consider the curve y equal to sine 2t, where now we've changed the angular velocity to 2. Now it's our omega in this case here is 2. Remember here, our amplitude was 2, our omega was 1. Now we've fixed our omega at 1, and our angular velocity is 2. And we want to see how that curve is going to move. So what I'm saying is, first step, look at your zeros. Now, this function is still sine. Now, if you look at the standard curve, it says it has got a 0 when the argument is equal to 0, isn't it? So, which means at that time, I expect this one also to have a 0 when the argument is 0. But what is my argument here? My argument is 2t. So, that must be equal to 0. Solving that equation, this gives me t equals to 0 over 2, which is equal to 0. So which means this function also is going to have a 0 when t is equal to 0. So that point is still on the curve. Are we together, guys? Where is the next 0? The next 0 is going to be pi. Which means it's saying that the simplest sine curve is going to have a 0 when t is equal to pi. Then I say, when argument is equal to pi. So I say now 2t is equals to pi. When I solve that equation, it says t equals to half pi. What does it say? It says now, this point is now is a 0 for this function, isn't it? Then the next thing is to look at the next 0. The next 0 is going to happen away at 2 pi. Then I say, when the argument, I always refer, in this case I'm not saying t equal to 2 pi, I'm saying when the argument of the function is 2 pi, now our argument is 2 pi, is 2t, 2t equals to 2 pi. Then this one says t equals to pi. So which means this one is going to be our final point for that cycle, isn't it? So which means now, instead of the function stretching up to 2 pi, the function is only stretching up to 1 pi. What does it mean now? It says it is faster in completing what? A cycle. It has actually completed the cycle in half the time it took before. Okay. So now we see that this graph is completed its cycle in half the time. Now once you've turned the zeros, you must go to the turning point. Now the turning points are when the argument is equal to half pi. So now you can say now here 2t equals to half pi. Solving that equation, you get t is equal to quarter pi. Then the next thing, let me draw a line here, just separate these two. You get 2t equals to what? To 3 halves of pi, isn't it? So 3 halves of pi, which will give us t is equal to 3/4 of pi. Then we've got to insert those values. We've got to insert those values. Now what we've got half pi here. That will be turning point. And there, that is when the function is equal to 1, isn't it? Because our amplitude is 1. So we've got that point there on the curve. And then 3/4 of pi, 3/4 of pi is going to be somewhere there. Then there, the function is when it's going to be -1. Now, when we do that, now to draw the curve, we try to draw a smooth curve up, that's the highest, down, lowest, then up. All together, that is the curve. Now, if you compare with that first version, the simplest version, what are we going to have here? The simplest version will go you see that because the angular velocity is 1, it's lower than 2, it takes a longer time, 2 pi, and then this one takes a shorter time, actually half of that, because we've changed that to 2t. Am I making sense there, guys? Is that right? Okay. This kind of discussion I'm doing here, you can do it when you've only changed the angular velocity, or we'll see later that we can do it also when we've changed like the phase, when we do horizontal shift of some kind to the left or to the right. We do exactly the same analysis. That the zero is here is half pi, the turning point is half pi, and the zeros are at multiples of pi. Are we together, guys? Okay. So I think at that stage now, I will invite you to go and maybe check this angular velocity to half, check it to 3, and just have an experience of what is happening there. Are we together? Okay. Let me. Right, now I want now to look at a different version of this curve. Let's say we've got y equals to sine. I'll leave still the amplitude 1. Then I've got pi minus pi. Now this is pi here, and just imagine that that curve is on the same axis here. You can imagine that curve being on the same axis there. You see where pi is a 0, and the 2 pi is our third 0 there. Remember, this from there to there, this is our period t equals to pi, and that is what we call one cycle of that periodic function, isn't it? It has completed a cycle. Now it would have completed a revolution. Right. So now I want to see what's the effect of this. Check what I'm doing. I'm saying I want to sketch this curve now. But to sketch a curve, what is most important is to get those points which are decisive in determining your curve. In this case, these points are the zeros and the turning point. The shape, we know the shape. All together. Okay. So then let's start with zeros. Zeros, we know the standard function is going to have zeros where? At 0, at pi, at 2 pi. Then we start repeating the same thing, isn't it? So now we're going to say this function is also going to be 0 when its argument is 0. But what is the argument? The argument is t minus pi equals to 0. All together. Then which means t is going to be equals to pi. It suggests that this function is going to have a 0 there. All together. Then actually what happens is that this 0 which was occurring at 0 has been shifted to the right and now is occurring at what? At pi. So which means actually the curve here will be rising like that, like it was rising there. I understand what I'm saying? Okay. Then the next thing is to get the next 0. The next 0 is going to be t minus pi equals to pi, which takes you to saying t equals to 2 pi. So now our next 0 is going to be there. Now what is going to happen there is what happened at pi, which means there the curve will be going down, isn't it? All together. Okay? Then the last one is when t minus pi is going to be equal to what? To 2 pi. And that will take us to t equals to 3 pi. So we've got something like that. Then let's insert our 1 there for amplitude and the minus 1 there. Now, if we're going to draw this function now, the turning points, we need the turning points, isn't it? We need the turning points. Let's say TP for turning points. Again, this function, the standard function, has got turning points. Let's say zeros there, for Z for zeros. TP for turning points where? At half pi, the first one from the starting point, half pi, and then the next one at 3 halves of pi. Are we together, guys? So now when we come here, we're going to say t minus pi equals to half pi. That will be the first turning point. Then we say t equals to pi plus half pi, which gives us what? 3 halves of pi. Are we together? Where is 3 halves of pi? 3 halves of pi is somewhere here. Then we get to the next turning point. I think it's clear. The next turning point will be 85 halves of pi, isn't it? Do the similar calculation, we get 5 halves of pi will be there. Now, what we've got to do now is just to mimic exactly the same thing which happened from there. That is our starting point. Up, maximum, down, 0, minimum, up to completing one cycle. So what we're going to do here, we just go these things, guys. It's very important to know how to do them manual first before you do them on the computer using a black box. Because you can draw this thing on a computer with a small program, whatever, but it's very sad to draw something on a computer when you don't know exactly what is supposed to happen. Are we together? Okay, so we got something like that. In the actual fact, let me extend this. This function, it will extend this way, into the left-hand side. It will extend this way. It will extend this way, to the left-hand side. Now it starts from somewhere minus infinity and they continue this side this way. All together. Then let's compare with the standard one. The standard one will go this way. It will go this way. Now, let's discuss something here. Just to check what's happening here. The starting point of the standard one is here, when the function shoots up here. But this one, the green one, it shoots up there. What's happening? The shooting up has been delayed by pi. It has been delayed by pi. By physical on the graph, what we see a horizontal shift of the curve to the right. All together. This is exactly the same thing I was discussing with you when we were talking about the parabola. We said that discussion we did on parabola, you must see how it happens in each and every function. So this is one function also where we are seeing that vividly happening, that it's going to shift to the right. So now, everybody should imagine what's going to happen now if I had a function like this one. Sine t plus pi. All together. I said to you, when you get a plus here, you must manipulate the sign until you reveal your minus sign, which is going to be minus pi there. So which means for this one, it says that your initial 0 is going to be minus pi. So now this shooting up here is going to be shifted to there. All together. Then, like I said before, I said you can read this minus sign as a kind of an phrase which says shift to minus pi. And then here shift to pi, or shift by pi, or shift by minus pi, meaning you move to the left. Is that clear, guys? So now I must be able, maybe in your next exercise, to give you any kind of this, whether it's sine or it's cosine. What I'm discussing here, you can just go and apply it to cosine, to tan, to whichever trigonometric function you get. All together, guys? Okay. Can somebody tell me what's going to happen here? Let's say, think about this one. Let's say now I've got y equals to 2 sine t plus half pi. What's going to happen then? You must be able to say in words, the amplitude is this, the phase shift is this, and then describe it verbally. Before drawing the curve, you must be able to describe verbally, this is what's going to happen. Or you just draw a rough sketch without a thorough analysis, we just visualize what's going to happen. Let's see, who is prepared to tell me what's going to happen there? Yes? By half pi. So the graph is going to be translated to the left by half pi, but the amplitude, now the waves are going to be higher, doubled from the standard, isn't it? Right. Then let's see. Let's come to this one. What's going to happen here? What do you think is going to happen there? What has changed? The amplitude has changed, isn't it? And I can also introduce something. The orientation of the curve has also changed. What's going to happen? Who can describe what's going to happen there? He's saying from the starting point, the graph is going to shoot downwards, isn't it? And then wrap around the axis as you go. All together. And then, what else is going to change there? Yes, my sister. Yeah. It's going to be shifted to the right hand side by 1, isn't it? By 1. Then, that's that. Altogether, sorry? And all these graphs we are seeing there, they are wrapping around y is equal to x. They are wrapping themselves around the curve, the line y is equal to x. Now, can you tell me what's happening now here? All what you have just said applies. Then, what is the new thing? Sorry? Tell me, it's going to wrap around y is equal to 4, isn't it? A line parallel to the x-axis, y is equal to 4. Normally, like y is equal to x, y is 0 there. Then we would normally say the average of that function is 0 because it's wrapping around 0. So now there, the average is going to be what? 4. Are we together? Okay. I hope at this stage, guys, everything, almost everything, not everything, but almost the influence of those parameters is understood. Summarizing what we've looked at, we've looked at the effect of the amplitude, whether it's higher than 1 or smaller than 1. We've looked at the effect of the phase shift, the horizontal shift, and now lastly, we're trying to discuss the vertical shift. So you must be able, when you're glancing at the sine curve like that, you must roughly say, without drawing to scale, but just sketch it around. This is to be more or less like this. Then you draw it neatly, knowing, having imagined how the solution looks like. I think I'm going to stop there and say thank you for listening.